Thank you, Doug. I think, yeah, technically I was a co-organizer, but I think Doug did all the work, or maybe Doug combined with the other co-organizers. In any case, I'm really happy to take part in this. It's been interesting to kind of watch the progression of numerical relativity and gravitational wave science over the last 20 years. I was at all of these meetings that have been mentioned by Doug and by Deidre, including some other ones that were more in the mathematical physics community that were relevant to LIGO. So it's been really exciting to kind of watch everything. So what I'm going to talk about, first of all, I should mention that some of what I'm going to talk about you can find written in sort of for a general mathematical audience in this bulletin of the AMS paper, but I will talk about some things that are in more detail than what's in this paper. Okay, so here's basically the outline of the talk, and basically I've got something in the talk for the different communities that are here. My sort of the way I'm classifying the different groups of people here, I know I have some people from the numerical analysis community that are specialists in finite element methods and geometric integrators, things like that. So I have some slides that should be interesting for you. I have some people from the numerical relativity community here that I'm talking to. I'm hoping that some of the things I'm going to talk about with the conformal method will be interesting for you because it impacts how you can numerically produce initial data using the conformal method. There's a lot of really interesting things going on with that problem right now. And I know there's some sort of general mathematicians, applied analysts here, and I'm hoping that some of the talk will be interesting to you because there are some really interesting sort of just pure mathematics kinds of questions that are that arise in mathematical numerical relativity, and a lot of these are really still open and being actively pursued right now by different groups. The first few talks are really for the numerical analysts who don't necessarily work in relativity. I'm going to give you my Cliff Notes version of the evolution and constraint equations in GR, and then quickly get down to the equations I'm going to talk about. So GR, so basically this is a little cartoon explaining sort of what's going on, our interpretation of what GR is doing for us as a mathematical model. So here's the Newtonian picture of gravity. We have a gravitational well given by Newton's law that is a gravitational attractive basin for a small mass that's flying by heavier mass. GR is basically a reinterpretation of this as a warping of space and time, although I'm only picturing the space here. And so the small mass actually just continues on a straight trajectory, which on a curved surface is geodesic, and the heavy mass is deforming the space and time locally. And we're all very familiar with now with all the excitement around LIGO and gravitational waves and so on, so I won't say much about these pictures here. You saw better pictures in Deidre's talk. Again, I'll kind of skip this slide, but basically these are two pictures of the detector in Louisiana, the detector in Hanford, Washington. Just a little bit about their sizes and so on, their designs. This is just a generic picture of an interferometer, which these detectors are based around, and there's a little depiction of the way the LIS detector would work. Okay, so and then just a quick summary of all the excitement that came from the 2015 detection of gravitational waves by the gravitational wave detectors. Again, I know we've all seen a lot of publicity around this, so I won't talk much about this. There's some great articles out there, both popular press articles and also technical papers about the details of these detections and the more recent things. Okay, so So let me talk about some of the mathematical problems that are interesting. So the Einstein equations. So this is a system of partial differential equations that describe general relativity mathematically. So if you want to, as a sort of applied mathematician, if you want to get a really quick sense of what the equations are, where they're coming from, what the different main components of the equations are, you can think about it in the following way. So if I have a vector field VA and I use this notation to denote partial differentiation, what we know from the calculus is in the flat world, we can commute partial derivatives as long as functions are smooth enough. So if you take a vector field and you're looking at its partial derivatives, you take another partial derivative, you can change the order in which you're taking the partial derivative. So a way to depict that is just look at the difference. I get 0. However, if I'm looking at a calculus on a curved surface, so basically I'm using ideas from differential geometry, and I do the same thing, then in fact I don't get 0. I get something left over, and that's because we have to define partial differentiation on a surface in a more complicated way using affine connection coefficients. So basically these guys here, or if we have a Riemannian manifold, then we will call these Christoffel symbols. So basically something that obeys its own sort of transformation rules on a surface is necessary in order to define a meaningful notion of differentiation or covariant differentiation. So when you try to commute derivatives on a surface, you get some stuff left over that's basically a bunch of terms like this. And we give that a name. It's the Riemann tensor. And if you were to just carry this calculation out, you'd see that this is what you actually get. If you were to take this guy and differentiate it and pay attention to all the terms and then try the commuting, you get this left over. OK, so that's the Riemann tensor. And you can construct other interesting objects by raising and lowering indices using the usual sort of ideas from differential geometry, using a given background metric. And so that's why I'm denoting these multi-index tensors with sometimes raised indices, sometimes lower indices. There's a canonical way to sort of move back and forth between them. So if we sum on some of the indices, so basically do a contraction, so sum on this index C here, then we reduce the order from 4 to 2, and that has its own name, Ricci tensor. And if we do this again, then we get the scalar curvature. OK, so if we combine these two things in this way, that's referred to as the Einstein tensor. And then if your space-time has some matter and energy in it, there's a canonical way to write down a stress energy tensor for that setup. And so the Einstein equations are basically just what's going on geometrically in space and time is determined by the matter and energy density. So GAB or kappa TAB. Kappa is just a constant that depends on the units you're using. And so I'll just sort of generically think about it as just some constant. The indices here run from 0 to 3, so time and space are represented there. We're just thinking about the three-dimensional world here. They're sort of all mixed up together in this equation. It's second order in space and time. It's not in any obvious way what we think about as a Cauchy problem without really staring at it pretty carefully. And early on, it was hoped that this could be reformulated in a mathematically precise way as an initial value problem, so basically a Cauchy problem, so that you could evolve something at an initial time forward. And if you've ever glanced at the book by Hawking and Ellis or any of the other sort of foundational books in mathematical relativity, that's essentially what the first parts of the books are about. It's the program to take this system and turn it into a well-defined Cauchy problem for certain classes of four manifolds, space-time four manifolds. And so that's so basically what you're doing is you take your four manifold, you restrict yourself to a class of four manifolds which admit foliations of by space-like hypersurfaces, which are defined in a very precise way. And so you can think about these slides I'm showing here, space-like surfaces that foliate in a continuous way this space-time manifold M. And these surfaces have well-defined normal and tangential vectors. And through this foliation, you can project the space-time system onto the space-like hypersurfaces and get at your Cauchy problem that you're after. Okay, so, and if you do that, I'm not going to write down the evolution equations, so you're going to see other talks this week that will do that. I'm going to focus on a subsystem referred to as a constraint equation. So what's going on with this system here is when you do this projection, you find that some of the equations are evolution equations, which take a spatial metric and its time derivative and evolve it forward in time. And some of the other equations don't have time derivatives. They're basically constraints on the initial data that have to be respected for all future time. So in that sense, the equations have a similar sort of structure to the Maxwell equations for E and M. Okay, so regarding the constraints, which there's supposed to be a T there. Missed that. Regarding the constraints, which I'll write down more precisely in a minute, there's a number of interesting questions that arise just having to do with the constraint equations themselves. So are there always solutions? If so, are they unique? Are the solutions smooth? How do they depend on the various data provided with the problem? Are there sort of standard PDE type estimates you can write down for the constraints that are really necessary in order to do any sort of rigorous numerical analysis later? So these are all kind of interesting questions, and then there's all the usual numerical analysis questions that follow. Okay, so let me just quickly get to the constraint equations that I'm going to focus on. So if you take the 10-component, if you take the 10 equations that are represented by G equal kappa T, and you do this projection onto a space-like hypersurface, you can think about that as producing 6 equations, second-order equations for a spatial metric, which lives on the space-like hypersurface, or a 12-component system for the spatial metric. So written in first-order form, a 12-component system for H, and it's something like its time derivative. So you can think about it either way. But in any case, what that means is you need to you have essentially 12 things you need to specify on the initial space-like hypersurface as initial data for this 12-component first-order system. If you look at the constraint equations, you have 4 equations. This is a scalar equation. The hats and the 3 are basically saying these are 3-dimensional quantities, so that's the scalar curvature of the metric that you have on the space-like hypersurface, which is projected from the 4-manifold metric. And then these are, this is the mean extrinsic curvature. This is the extrinsic curvature. And this would be matter field on the space-like hypersurface. Kappa is from the Einstein equations, and so on. So this equation here is basically a scalar equation. And this, because we're in 3 dimensions, this is the divergence, or rather the gradient of this scalar field. So this is basically three equations. So you have 4 equations total, specifying 12 degrees of freedom. And so it's underdetermined. The initial data is basically underdetermined. So there are different ways you can specify the 8 missing pieces of the initial data and then use these equations to recover the remaining 4. And this was studied for many years. And in the 1940s, a particular way of specifying some of the initial data in the case of constant mean curvature foliations was given by Lichnerovich. And then this was then sort of expanded by York in the 1970s. And this is generally referred to as the York conformal decomposition now. So basically the idea is you specify a background metric. That's the H here, and then you think about the space-like metric on the space-like hypersurface as conformally related through an unknown function phi that we'll determine with the constraint, this constraint here called the Hamiltonian constraint. And then there's a piece of this extrinsic curvature that you are going to determine from this equation. You're going to specify the other pieces in the following way. So I'm not going to dwell on the details here, but this particular, so why this particular strange-looking decomposition? Well, the idea was you want to engineer the choice of the parts of the initial data you're going to specify so that these two equations produce nice elliptic spatial type partial differential equations where the principal parts look like familiar, nicely behaved second order elliptic operators. So that's what you get when you plug in this decomposition into these two equations. You get this equation here called the Hamiltonian constraint, which has the Laplace Beltrami operator on this scalar function phi plus a bunch of low order nonlinear terms. And then similarly, you have this well, if you look at this operator here, there's a divergence of something that looks like a strain tensor. So it looks something like the linear elasticity operator plus some low order terms. And they're coupled together. W appears in this equation here as a source term, and phi appears as a source term in the second equation. If you stare at this looks like a linear strain tensor. In fact, if I put a mu in front of this term and replace minus 2/3 with lambda, that would be the linear elasticity operator for isotropic homogeneous material. So this is a familiar looking operator. And the notation here is just I'm kind of using the conventional notation. This is covariant differentiation. That's the comma is the partial differentiation, and the Christoffel symbols are the affine connection coefficients come from the metric. Okay, so that's that system. So I mentioned this paper of Lichnerovich in the 1940s, and so once this this program for trying to understand the problem as a Cauchy formulation was sort of studied, and progress was made, and eventually this sort of seminal paper appeared by Yvonne Choquet-Bruhat in the 50s. This was basically her PhD thesis, I think, where she proved the first essentially local in time existence theorem for the Einstein equations as a Cauchy problem. And I should mention when the last time I was here was 2005, and she was at that meeting. She was actually my office mate for a few days. I was only here for a few days. And I just started working on the constraint equations, so I got to meet her at that meeting. And then later, when I published the paper I'm going to talk about in 2009, she sent me a nice email about the paper. And it's sort of, in some sense, one of the highlights of my career was that little email she sent me. Anyway, so she used this decomposition idea in her work, and as I mentioned, this was expanded on by York in the 70s to try to think about how to specify initial data. And then this was studied as a mathematical problem, by essentially PDE-focused people. And Jim Eisenberg was a seminal and is a seminal player in that area. And he published a number of papers on this problem, so analyzing that constraint system when the decomposition is used. And this 1995 paper is kind of a seminal paper in that it summarizes all the constant mean curvature cases and sort of finished off the problem. So the case where you have constant mean curvature slices is very important because the two equations decouple, and I'll explain that in a second. And that paper kind of summarizes everything that was known by 95. And when the two equations coupled together, there was a single result that Jim Eisenberg was involved in with Vince Moncrief from 96. But unfortunately, that was sort of the end of progress in that area until 2008. So how did I start out working on this? Just very quickly. So I was a postdoc at Caltech during the sort of early phases of LIGO, so I was exposed to what was going on there. In fact, Kip Thorne, my postdoc advisor was Herb Keller in the applied math group, and he wanted to write a paper with Kip Thorne, so he sent me to Kip Thorne's GR class the first year I was there. So that's how I got exposed to this stuff. I got really interested in the problems that arise there. But it was clear as I'm not really in a large physics group. I wasn't coming from a large physics group. I needed to peel off a well-defined problem that a single assistant professor starting his job at UCSD could work on. So I basically decided to work on the constraints and to see if there was something I could do there. And it was the basis for my first NSF proposal when I got to UCSD in 98. And so here was my plan in 98, basically figure out a very completely mathematically, completely rigorous, well-defined boundary value formulation of the constraint equations. And I was thinking only the conformal method at that point. Nailed down everything that was known about the solution theory, a priori estimates, which you usually find in the PDE literature on any kind of mathematics problem that involves elliptic equations. And then just use everything in the literature to do this set, which is the stuff I would normally be interested in. So basically come up with some finite element method, write down a priori error estimates, so I have a convergence of the method, and then make sure the discrete problems are well behaved. So maybe some sort of discrete existence theory. If necessary, it's a nonlinear problem, so strange things can happen. Write down a posteriori error estimates for doing adaptivity, design adaptive algorithms around that guy, and then design solvers, fast solvers, some kind of nonlinear solver, fast linear solvers, do things in parallel, publish papers. And unfortunately, my plan didn't really work because it turned out that the 1, 2, and 3 was kind of up in the air. Even 1, what's the correct boundary value formulation of the conformal method? That was not well understood. In fact, the papers only came out in 2004, where people like Sergio Dane and David Maxwell started looking really carefully at what the right boundary conditions were for things like black hole models. So, and there was, as I mentioned, there was very little known, essentially nothing known about the coupled case until, other than this sort of very specialized result that I mentioned from '96. So in the end, I sort of worked on both of these tracks simultaneously, and I wrote an early paper trying to do some of this stuff here for finite element method for the 2 constraint equations, where I just had to assume, I made conjectures, they're stated as conjectures in the paper about there's a solution, it has this regularity, I don't know if it's really true, hopefully someone will prove that theorem soon, and then I just wrote down some things like standard error estimates. Okay, so here's the more mathematically completely specified version of the conformal method. So basically the Einstein constraints using conformal decomposition as a way to specify everything. So I've written things down here in a more concise way, where L is basically the Laplace Beltrami operator. This boldface L is that elasticity type operator. And then the 2 F's are the coupling terms. And if this is happening on a 3 manifold without boundary, then that's it. But if there is a boundary, either an exterior boundary, or maybe I have an interior boundary with black holes, or maybe I have both, then I would have some kind of boundary condition like this. And this is sort of the most general type of boundary condition that people end up using for modeling. And I'll come back to this nonlinear Robin-like term a bit later. But so the notable things here, well, the boundary condition terms here are important later. But the notable things are the coupling terms. So AW is my sort of shorthand for the coefficient in the Hamiltonian constraint where W appears. And then the B tau term is my shorthand for the term that multiplies the coupling term in the other equation. And again, my notation is the same as it is on the other slides. So this is just a standard geometric PDE using pretty standard notation. The principal parts are linear, second order, and then there's the low order nonlinear parts. Okay, so I mentioned just briefly some of the key papers, but maybe just diving down a little bit more detail. In the case that you have constant mean curvature, that's what this is noting here. The mean curvature tau, the mean curvature of the 3 manifold tau, is constant, so its gradient is 0. And again, that's this guy here. B tau is where this shows up. So when that happens, this term that couples this guy to phi drops out. So you can just solve this equation without any regard to phi. You have W, and you do that once, and then you plug W in, and you can solve for phi. So in that sense, the 2 equations are completely decoupled, and all the theory for the existence theory for the 2 equations was done using that assumption through 95. That's referred to as the CMC, or constant mean curvature case. And I mentioned some of the key papers. I mentioned the York paper, which is really about the formulation of the conformal method. But he worked with Niilo Murhu on the actual existence theorems for the Hamiltonian constraint. These were the sort of first papers on that. And then I mentioned Jim Eisenberg's seminal paper. The non-CMC case, so this term no longer drops out. The two equations couple. And there were no results until the 96 paper where Jim Eisenberg and Vince Moncrief showed that if you assume that that coupling term is really small, that's referred to as the near CMC paper, or near CMC condition. So if you think about it, what that means is it may not be 0, but in some measurable sense, like some particular norm that shows up in the way the analysis is done, if this is small, say point-wise or in some other measure, then the coupling between the two equations is really weak, and then you can show that there's a solution to the coupled system. And all of the results for the next 10 years use that framework. So all of the results that are not CMC were basically the near CMC setting. So just a comment here, because this shows up if you ever try to look at any of these papers and understand what they're saying, just even the statements of the theorems. There's a sort of a common way to think about three manifolds, and in terms of what kind of three manifold are we talking about, and the way the people prove theorems about PDE on three manifolds. It turns out that what class the metric for the manifold is in is a crucial determinant of what kind of theoretical results you end up being able to show. And so Yamabe classification of metrics ends up being important. And if you read any of the basic theorems, even the 95 paper by Jim Eisenberg, the results are all stated in the following way. If you have a positive Yamabe metric, then the following is true. If you have a negative Yamabe metric, then the following is true, and so on, if you have a zero Yamabe metric. And it turns out that the metric for every three manifold can be disjointly classified in the following way. And it comes down to what I wrote here in kind of a high-level way. Basically, what is the Yamabe problem? It's basically if you take a smooth metric on a three manifold and you take a positive function, you multiply the two together, and then you look at the scalar curvature you get in the way I described in the earlier slides from this guy, and you look at the scalar curvature you get from this new guy, then they're related like this. And so you can turn this around and you can say, well, if I can solve the Yamabe problem for a given metric h, meaning I could find a positive function u which satisfies this, then I've shown that the two metrics are related in the way I've described here. And so this is why this is considered an important problem. The sort of true Yamabe problem would be maybe if I actually require RU to be the constant 1, for example. So basically metrics of constant curvature 1. In any case, so now you know basically what it means to say I have a Yamabe positive metric. It's just a way of thinking about things. It turns out that the literature is not very complete on this. So for example, if the metric you're talking about is not smooth, then the Yamabe problem is actually still open. And it turns out that you can still work with this idea even though that's still an open problem. And that's one of the things that are in some of our papers. OK, so just a really quick look of how you say things about the conformal method in the case that the two equations couple together. Basically, the main idea that most of the papers that analyze this problem, the way they think about this is they construct a fixed point iteration that involves solving one equation and the other and just iterating back and forth. And so basically, if you compose these two maps, S and T, you get a map which I'm calling here G. And the main theorem from 96 was that this map basically is a contraction type map. And the near CMC condition was basically a way to engineer this map G so that it contracts. I'll just leave it at that. OK, so now I've kind of summarized everything that went on through 2007 for that method. Now what I'm going to do is very just quickly explain what we worked on. I'm going to take maybe 15 minutes here, maybe 10 minutes here, and then I'm going to move to some of the things we worked on having to do with numerical methods for the constraints. OK, so what we focused on was looking at when showing that you could solve the constraint equations without any conditions on the mean extrinsic curvature. So we didn't want to consider this near CMC case. We wanted to think about the completely general case. So the idea was to somehow come up with some sort of argument that would allow you to show that there's a solution to that coupled system with no conditions like that. And so that was the content of these two papers. The papers actually, the main paper is this paper that appeared in Communication Math Physics in 2009. This paper here is just a 4-page summary of a simplified version of the thing, but it's easy to read. So just briefly, what's going on here is if you sort of engineer a slightly different version of that map G, and you use different analysis tools, basically topological type fixed point arguments instead of the arguments that they had been used originally, then you can remove the near CMC condition. And I don't remember if okay, so here's just a really quick look. I'm trying to not to have too many really dense slides, but this is sort of for the PDE, numerical PDE people here that might be interested in how this works. So if you construct this this composed map G in a slightly more general way than what was used by Eisenberg and Moncrief, so basically this is again just my constraint equations. This is all happening on a closed manifold for the moment. There's no boundary conditions. And these maps here are now a little bit different than what I defined earlier. This is now the Laplace-Beltrami operator plus a positive shift. So it just allows me to remove a kernel. That if I'm on a closed manifold, that's actually an issue. So there's a little trick, a little shift trick you can do to get rid of that. And just you incorporate the shift in the other side of the equation also. It's not a problem. And so you construct this map T that's now a little bit different. It's not the solution map for the Hamiltonian constraint anymore, which is what Eisenberg-Moncrief used, but it's actually a Picard map. The reason you do this is that this map's much easier to make estimates for. You can say a lot of things about this map because it only involves inverting a linear operator that you have a lot of control over. Anyway, this is sort of the first idea, and then you compose these two to form this map G. And then just very quickly, the idea is you base your existence theorems on a more general fixed point argument that just involves showing that the map, the composed map you have, just has some general compactness properties. And so this is kind of the main theorem that's now used for the Einstein constraints, I would say, in terms of the far from CMC case or the non-CMC case, just this theorem here based on compactness arguments. Okay, so I mentioned, so that's basically the content of these two papers was laying out that new framework. And then all of the subsequent results by our group and others have been based around that kind of more general idea. And so what's been done since these papers on closed manifolds in 2009? Well, basically, as had been done for the CMC case, to try to do some of the other things that are interesting, like rough metrics. So this was interesting for people studying the evolution problem. When can you solve the Einstein evolution equations when the data you're dealing with is not very smooth? And so there were a sequence of papers in the early 2000s which had the words rough data, rough solutions to the Einstein evolution equations in them. They were based on assuming that you could solve the constraint equations with rough data. So that was a kind of a program that was launched by David Maxwell, and in fact, eventual worked on that also. And there were papers for the CMC case on that. And so what we did was, in that same 2009 paper, we actually considered the rough case and the smooth case at the same time. And so our theorems were actually for rough metrics or smooth metrics. Okay, this is, I'm just going to state, just so you have a sense of, if you look at one of these papers, what one of the theorems might look like. And I only have a couple of theorems that I state like this in my talk, just so you get a sense of it. So that you basically would say, you're starting with you have a three-dimensional Riemannian metric, you state some smoothness assumption on the metric for that three manifold. The no conformal Keeling fields assumption is common in all the theorems on the conformal method, and basically it's excluding the kernel that could appear in the Hamiltonian constraint, that linear elasticity type operator. I'll say more about that in a bit later, because one of our most recent papers, we come up with a way to get away from that assumption. Okay, and then there's an assumption about which Yamabe class that metric's in, which I explained. And then there's the requirements on how smooth this metric needs to be. That's relevant to people, the people that are interested in rough metrics, how rough you can make the solution. So it's very complicated conditions on various coefficients, but the bottom line is using that fixed point argument, that new framework, you can prove that there's a solution. Okay, so you can even do things more generally than this. So I won't say anything about this. We only looked at this briefly. Caleb was a student. I should say that, I forgot to say this. These different colorings of names, the red is, these are PhD students I had, and the purple or magenta, these are postdocs that I worked with. Okay, so Caleb's thesis involved, one of the things he worked on was, can you use this kind of really strange idea of Colombo algebras to get past the problems with multiplying distributions? It's kind of a funny thing that it's a really general way to think about elliptic equations. It's interesting. There's probably only about 5 people in the world who would be interested in that. But if you are, it's, there's a paper. Okay, but so basically, let me cut to the chase here so I can get a little bit to things that might be interesting to people doing numerical methods. You know, the other cases that you would be interested in are the compact with boundary case. I mean, this is the most relevant for numerical relativity. You want to produce initial data on something like a sphere with some spheres cut out of it, so you want to do a black hole binary simulation. So this is the mathematical formulation you care about. And it took until 2018 for us to actually come up with everything was needed to do that case. This was the case we started with, but we abandoned it and went to the closed case until we could resolve the difficulties there. And so this 2018 paper finally came back to doing the case where you could have a sphere with one of these general row band type conditions on the outer boundary for both the Hamiltonian momentum constraint and then interior boundaries that are modeled as black holes. I have a few slides on that because this is basically coming from the original York-Perrin idea of how to model asymptotically flat manifolds. So this is what a type of boundary condition you would put on the exterior boundary. And then there's the papers by Sergio Dane and David Maxwell that I mentioned on how to deal with black hole interior boundaries. It turns out that the way they approach this, it looks very different in their two papers, but they can both approaches can be viewed in the way I wrote down the constraints earlier. It's just a way to define this KW function that I highlighted in the earlier slide. And it turns out that you can write it in this form, and you can capture both of their frameworks in this way. Anyway, there's a very complicated analysis that is done in both papers that you can capture in our setup here. And the interesting thing that happens, unlike the case of closed manifolds, is that even if you have constant mean curvature manifolds, the two equations actually still couple through the boundary conditions. So they never decouple, which is not a widely known thing. So if you're just solving the Hamiltonian constraint because you think you're okay with constant mean curvature slices and you have boundaries, then you're actually making a mistake. The two equations couple, you have to solve them at the same time. So some of the highlights in this 2013 paper where we considered just how to capture the black hole boundary condition stuff in one framework and prove theorems about the Hamiltonian constraint. There's a number of sort of supplementary results that are needed to handle the full case that are in that paper. So what about the non-CMC case? That's what's contained in this most recent paper. Basically, it leverages all the stuff that we put together in the 2013 paper for just the Hamiltonian constraint and analyzing the boundary conditions. And then there's, again, a couple of additional results that have to be put together. And the hard part of that paper was how to deal with the fact that the coupling happens now in the boundary conditions in addition to the interior. I mentioned this earlier. It's one of the things you have to sort out, even to write down a theorem for the case where you have boundaries. You have to think about what it means to classify metrics. And there were the Yamabe problem was examined on compact manifolds with boundary by Escobar in the 90s, but it was only for smooth metrics. So again, that's another open problem, just the Yamabe problem for rough metrics on compact manifolds with boundary. But it turns out you don't have to solve the Yamabe problem. You can still classify Yamabe metrics. You can still make sense of disjoint Yamabe classes in the way that we describe in our paper. Okay, so what are just a brief summary of other things? So other things you might want to know about, because this is relevant to the actual sort of physically most meaningful models. If you have an asymptotically Euclidean domain, so you don't truncate the boundary, so mathematically you want to understand what's going on if you have black holes in the interior or not, and then you have asymptotically Euclidean manifolds. Well, then the idea is you're still interested in whether you can solve the constraint equations, whether you can deal with far from constant mean curvature foliations, and so on. So that's what those papers were about. And then there's an interesting story that sort of started to happen that it goes back quite a ways. So people in numerical relativity who were using the conformal method noticed that when you solve the coupled system together, that you can generate more than one solution, which seemed very strange, since all the existence theory for the for the Hamiltonian constraint by itself, the constant mean curvature case, showed that it was always well posed. So there's not just a solution, but it's always a unique solution, except for some really degenerate situations. But it turns out numerically you could show that there was sort of this classical fold type behavior for the coupled system. And so we started actually studying that. It turned out to be a really interesting development in the theory for the conformal method. So a number of people have looked at that. So our first paper on this was just doing numerical bifurcation theory using the stuff that I learned from Herb Keller at Caltech, just using pseudo-arc length continuation and the auto package, and just showing that, yeah, you do have a fold in some versions of the conformal formulation. And then my student Caleb, this was the second part of his thesis, he actually looked at this from an analytic bifurcation point of view, so actually trying to prove that you have multiplicity of solutions. And then we examined this a lot more carefully with my colleague David Maxwell, and then James Dilts, who was a student of Eisenberg. He came to do a postdoc with me. And these are very much more recent things. And then finally, regarding multiplicity, so the kind of the end of the story is that because of this behavior, the fact that the conformal method admits multiple solutions, and it has some other, and in fact, it also you can state the conformal method for physical situations where there's no solution to the conformal equation. So, so in other words, the conformal method away from the near CMC setting is basically a broken way of specifying initial data. And so in some sense, it's kind of a failed method, other than the CMC and near CMC case. So people have started to look at different parameterizations of the initial data that depart from the conformal formulation. And there's a sequence of papers that David Maxwell wrote that he comes up with a new system referred to as the drift system. And there's very little known about it, but it's a different parameterization of the initial data. That's a different way of specifying the eight pieces of the data that you're not going to use the constraints for. And this paper here was an attempt to analyze this, produce a solution theory, at least a partial theory, for this new system referred to as the drift system. And one of the interesting things about it is his system allows you to prove theorems about the constraints that don't involve having to make assumptions about conformal killing vectors being present on the manifold. So it actually gives you a new theory that is outside of the conformal method. Okay, so I'm going to kind of skip the details of that. I'll just mention my student Ali is really interested in some of these side things that show up that end up being obstacles. If you really want to do everything carefully in these papers I'm talking about, it turns out that even the literature on when you can multiply functions together in some of these settings is not complete. It's basically a bit sparse. And so, in fact, we need some results that are not actually in the literature. So my student Ali spent a lot of time on trying to understand some of these things. So those things are not published yet, but they're all in the archive. Okay, so I've only got a few minutes left here. So I just want to give you a sense of what that sort of second track of research involved. So as I mentioned, I wanted to do kind of the standard numerical analysis stuff where I take the constraints and I can construct finite element method, write down a priori error estimates, things like that. One of the challenges is that the problem's happening on a surface. So I'm talking about, again, if I just think about the Hamiltonian constraint, a problem that looks like this, although it may be coupled to a problem that has this as the principal part, or something like that. And so this was the paper I mentioned where I wrote down a priori error estimates for the Hamiltonian momentum constraint, just making assumptions about the solution theory for the two equations. And then I kind of took that side trip on just studying the equations, but then finally came back to this from the numerical analysis point of view when Ari Stern, who's here at this meeting, came to work with me as a postdoc. And what we looked at was sort of how do you deal with the fact that you're discretizing the problem using a triangulation of the surface and not the actual surface. So what does that mean exactly? Well, I mean, you could do that without regard to any special discretization or new sort of fancy new frameworks like the finite element exterior calculus. But my own interest was I wanted to understand the finite element exterior calculus. We wanted to solve a PD on a surface, so we ended up sort of combining the two things together as a project. So, the finite element exterior calculus, since you're going to see talks on that this week, I'll just have a couple slides to get you oriented on that. This is now for maybe the people from physics who are not very familiar with this stuff. So let's just look at this for a second. You have the vector Laplacian, and you say you want to solve the vector Laplace equation. Natural variational formulation, these are just the appropriate sets of spaces for the vector fields that you're working with. For this to make sense, this is kind of a standard Galerkin formulation. This is just a weak formulation of this problem where I've done some integration by parts on the higher order part here and just written down what you get. Now, this is one way to think about the problem. This is sort of the equivalent of taking the Poisson equation and putting it in weak form. But you could also alternatively take this problem and think about a mixed formulation, which basically involves defining a variable sigma, which is basically the first derivative of u, and then writing a first-order system for the two together. And this is referred to as a mixed formulation. And there's at the moment, there's no real need to do one versus the other, no motivation. In fact, the second one looks complicated. But it turns out that if you actually just apply the finite element method to both formulations, the second one works extremely well, and the first one has some problems. And this is explained in great detail in the papers by Arnold, Falk, and Winther in 2006, 2010. It's awesome that all three of them are here at this meeting. And anyway, I'll just refer you to those papers if you want to understand this a little bit more. I just have a slide here, and my slides will be available if anybody wants them. It just kind of explains what's going on and what the connection to topology and geometry is. It helps to explain this. Again, it's explained much better in their papers. It turns out that if you want to leverage or exploit what's going on with mixed formulations and understand it from an abstract point of view, it turns out that the proper sort of setup is what's referred to as a Hilbert complex. And so the idea is you have a sequence of Hilbert spaces which are connected together by linear maps that have certain properties, and together these things form a complex if the maps have certain properties. As Hilbert spaces, there's an inner product floating around, and you sort of have there are really two spaces that are kind of mimicking what happens with L2 and H1. And this is an abstraction of this complex that appears throughout all of mathematical physics that involves grad, div, and curl operators. I'll skip this slide since I'm pretty short on time. I want to just at least summarize a couple things that we've worked on. But basically, you can dive into this in a little detail. That is an abstraction of what's going on with this sort of standard complex that shows up all the time in physics. And you can interpret that mixed formulation that I wrote down in this abstract setting as looking like this. And then let me just cut to the chase. This seminal paper by Arnold, Falk, and Winther, and then this the one that they wrote later, one of the main results in that paper is basically that if you have such a differential complex set up and you have a subcomplex which is related to the PDE level complex by maps which have certain properties, then you get immediately an a priori error estimate for a Galerkin method using the subcomplex. And the value of this is that it helps explain why certain finite element methods are stable, because stability is one of the requirements to be able to write down estimates like this. But maybe more importantly is it actually gives you a framework for coming up with finite element methods which are guaranteed to be stable. So the development of the finite element exterior calculus is one of the most exciting things that's happened in numerical PDE in 30 years. So it's really quite interesting. Okay, so just very quickly, if you're going to use a framework like the finite element exterior calculus, and you're dealing with the fact that you have a surface, you have a three-manifold, that's your space-like hypersurface, you want to solve the constraints, you have to use a triangulation, and you have to work on the triangulation. You can't work on the smooth manifold. So what does that mean? What's the implication of that? Well, if you take your PDE problem on the surface, you have a variational formulation of it, just weak form of your Hamiltonian constraint, for example. You have a Galerkin method. Now you're working with the triangulation. What that means is that the subspaces that you build, piecewise linear functions that represent a subspace of H1 typically, they're no longer being defined on the right domain, so you're no longer actually working with a subspace. And this is referred to as a variational crime. So your discrete problem looks like this. You're no longer projecting into a subspace in any Galerkin kind of projection sense, and instead you're doing something else. It's sometimes called an exterior approximation. And this is referred to as variational crimes, and there's a mathematical framework for sort of analyzing that. It goes back to the very early days of the finite element method, where you're even interested in things like you want to solve a problem on a disk, you have to use a triangulation of the disk. So how do you analyze that? Okay, so in any case, you can do this kind of approach with finite element exterior calculus, and instead of having subcomplexes, you have a complex which is related by more general maps, not inclusion and projection. And as long as those maps have certain properties, you can write down a similar kind of a priori error estimate. And these maps, these extra terms that are not present in the original Arnold Falk-Winther paper are basically telling you what these maps are doing. And so this is the content of one of the main results in the paper with Ari Stern, the first paper. And the interesting thing from our point of view was you can actually use this framework to recover the complete surface finite element method, which had been, this is a method that had been designed specifically for writing down numerical methods for solving PDE on two surfaces, and with a complete analysis framework giving you error estimates, a priori error estimates. And Alan Demlow has a number of papers on the surface finite element method that it sort of extends it to the three-surface case. But what our paper was able to show is that you can recover all of the surface finite element method results for 2 dimensions and generalize them to arbitrary spatial dimension and to more general domains. And so that's essentially the content of the project with Ari. And the second paper basically extended this to the semi-linear problems on surfaces. And as far as I know, that was the first a priori error estimate type result for finite element exterior calculus for a nonlinear problem. Okay, so some of the other things we worked on, I know I've only got like 1 minute left, just so you can get a sense of the trajectory of this part of the program. I've really been interested in adaptive methods, and so this is a separate set of projects that involved analyzing the convergence of adaptive methods for semi-linear problems. Long Chen was a student of Jinchao Xu, came to work with us as a postdoc. And also Yunreng Xu was similarly came out of Jinchao's group. Anyway, so we had a sequence of papers where we were looking at when you can show that adaptive methods converge. We were specifically interested in goal-oriented methods, which is kind of maybe a really nice way of thinking about adaptivity for practical problems. And then finally, the idea was to use adaptivity in the finite element exterior calculus setting. So this is one of the open areas in finite element exterior calculus, is to do adaptivity and prove that you have convergence of the methods that you're working with. So this is a sequence of very recent things, and including something with Martin, who's here at this meeting, who's currently at UCSD as an assistant professor. And the idea here is to formulate adaptive methods and put together rigorous proofs about convergence of adaptivity in the final mixed sphere calculus setting. And then finally, this is my last slide. So there's also interest in extending the final mixed sphere calculus to evolution problems, and we're going to hear about that later this week. I think Doug's talk is, I think, about some of these kinds of things. I don't list it here, but Doug has a seminal paper on exactly this that's cited in our papers. But basically, the idea, what we looked at was if you do sort of a method of lines discretization of parabolic and hyperbolic problems, and use the final mixed sphere calculus for the spatial discretization, and then you sort of use the standard ODE kind of theory for the other two, for the time dimension, what can you do for writing down error estimates? And that's what is in these two papers, and I can just leave it at, you can recover all the classical results from Baidar-Tomei and Gavecci on method of lines, but in addition, you immediately get the extension to arbitrary spatial domain and more general spatial domain topologies than what appear in the literature. So you do get value from the final mixed sphere calculus in that way every time you do this. And then there's some very recent things that we have in preparation. I think Evan is supposed to be here this week, and maybe these papers will get submitted this week then. But these are basically about what if you have a moving surface. So the surface itself is evolving as you're solving a PDE on it. And then there's a technical thing that's needed for almost all of these things that we looked at. So if you want to know more about any of these topics, I have an extended bibliography that explains all the literature on, or the points you to the right literature on the different parts of the conformal method, the CMC and the non-CMC theory, some of the key recent papers, and then our papers on rough solutions, multiplicity, ours and other papers on this kind of new framework. There's a completely different thing I didn't have time to talk about that's related to all this. It's referred to as the limit equation approach to the conformal method. It's a really interesting new direction that's still not completely understood. And then these are some related papers. Romain Gicot is someone that I'd hoped would come to this meeting, but it didn't end up working. But he's doing some of the most interesting recent stuff on the conformal method. Okay, so I'll leave it at that. Take questions.
Are there any questions? Warner?
So you've mentioned this, the non-uniqueness of the conformal formulation of Holst. If you look at an example where you have two or more solutions, is there any, if you can expand on that, is there any notion of them one being non-physical, or when you look at it from a physics point of view, what are the characters of those? With the other newer formulations which are non-conformal, have you looked at it with those formulations, and what does that say?
Well, so I don't have a good answer for you. At least I have no intuition about which one is physical and which one is not, other than one of the solutions generally comes from perturbing away from CMC or near CMC. So maybe in some sense that one you might call the more physically relevant one. At least it's closer to the intuition for CMC and near CMC. The paper that I think it's in one of these slides here. Yeah, this paper here that James Dilts, the student of Eisenberg, did as a postdoc with me. It's not accepted yet, but it's on the archive. This one, we actually look at the drift system a little bit. It's mostly focused on the conformal method. But the first thing that occurred to us also was, well, is the drift method, does it also have these degeneracies? And it has a lot of problems too. It doesn't get away from all the problems that the conformal method has. It has another set of problems, just in terms of showing that there are solutions and so on that are much more challenging than the conformal method. so this paper is it basically is a really complete numerical bifurcation analysis of the conformal method. It just looks at every possible parameter range and looks at all the different parameters. And, I think it's a pretty good explanation for why the conformal method is broken.
So how does this grid system avoid the eventual, no conformal fields problems, and what are its equations look like?
It actually is sort of it looks like a generalization of the conformal thin sandwich method. I don't have a slide showing the equations, but I can actually talk to you about that, David, after. I can go through the paper with you, actually. In short, the way it gets around the conformal killing vectors assumption is it's based on kind of a different way of analyzing the constraints. It's actually due to Gicot of instead of well, you can basically use an implicit function theorem like argument instead of the Schauder type argument that I mentioned that was sort of key to the far from CMC things. The implicit function theory argument has a way around the conformal killing vector assumption. I'll just leave it at that.
Other questions? So I have one. So all this fancy stuff for existence and uniqueness and lack uniqueness and so forth about the conformal method. But ultimately the numerical people have to pick some initial data that they represent some physical situation. So I guess they have to pick the quantities that you're allowed to pick, and they have to pick the boundary conditions. Does this theory help them do that?
I would say that this helps steer you away from problems in the sense that we're basically saying you have to use CMC or near CMC settings, or you can't rely on the conformal method to give you initial data.
And is that good enough for the physics? That enough what you need? Okay, well maybe there's a question we can revisit as we have discussion.
Well, so there is an open mathematical problem that is do all spacetimes admit constant mean curvature foliations? It's actually an open question. And in fact, James Dilts and I wrote a little paper on what's known and what's not known. So it's relevant to exactly what you're asking.
So and if the answer to that is no, then you might be missing
Yeah,
physics.
exactly. Yep.
Okay, so we are on lunch break until 1:30. The schedule said lunch at, which is it, Edmund College? Edmund College, which I think is about a 15-minute walk. I have the cafeteria. I guess that's just an informal lunch anyway, so you know more about that. So I would suggest that if you're one of the locals who've been here at the Institute for a while, make yourself available to people who got the 15-minute walk out to get there. That's where we're going or somewhere else. If you're not a local, you might want to try to grab one. Okay, so 1:30.